So let's begin. First thing I want to know is what is the discrete time Fourier transform of all right, here's a discrete time signal. What's the Fourier transform of this? What did you say? What did you say? A sigma field? What? What's the Fourier transform of this? What? Okay. I don't mean the Fourier transform of the picture. I mean of this right here. Come on. This shouldn't be that hard. I'm going to get the picture ready. Okay, what is it? Well, if it was a continuous time function, if n was replaced by t, what would it be? It's a delta function at frequency f naught. So if it was continuous time, that's what it would be. Now, it's a discrete time signal, and there's something we know about the Fourier transform of any discrete time signal. What? Oh, I saw you mouth it, I think. What do we know about the Fourier transform of a discrete time signal? It's periodic with period 1. So it can't just be this. Now remember, the way we verify in continuous time that this is the Fourier transform is by using the inverse. Very easy to plug this into the inverse Fourier transform. Let's come up with a guess. It has to be periodic. So let's put delta functions in a periodic extension of this. Okay? Do you think this might be the Fourier transform? And, well, again, let's just check using the inverse Fourier transform. So, all right. And what we should do is we should integrate over just one period. That's how the discrete time inverse Fourier transform works. This function here whoops, shouldn't have a t, should have an n. Okay, now, of course, only the delta function that's within that interval matters. So one of them will be. It may not be f naught. F naught might have been really big, okay, but there's going to be one of these delta functions exactly that falls in that interval. All right, so this is going to be exactly, and then integrating with respect to a delta function is easy. So I'll say it's e to the I 2 pi f prime n. Okay, where here's what we know about f prime n. F prime equals f prime minus f is an integer, and f prime is in that interval. Okay, so this is just how I'm identifying which delta function is there. Why do I say f prime minus f is an integer? Well, each of these was an integer away from f prime, right? We're just looking for the one that fell in that interval. And that's the key here, because if f prime minus f is an integer, then we can say by aliasing, this is equal to e to the I 2 pi fn. Do you get that? We just said that it's an integer difference. These are two formulas, two aliases for the same signal. Okay, so there we verified that this is the discrete time Fourier transform of a delta function. Now what we notice is these other delta, we wrote it as if it was just had a frequency f naught, and yet these other delta functions just appeared there. And that's the whole idea of aliasing in picture. It's that these are indistinguishable delta functions. They're indistinguishable signals. These frequencies are exactly the same in discrete time. Okay. To drive that point home, let's just look at a problem you did in problem set 3, problem 5. Okay, this was the optional problem set, and we said, and the question was, show that sine n can be written as some other sinusoid, and the answer was, it's sine of 1 minus 1 over 2 pi n. Okay, but let's just look at that graphically. So sine n can be split up. Sine n, now we usually think in terms of frequencies, and there's a 2 pi missing, so this equals sine of 2 pi, and the frequency is 1 over 2 pi. Okay, so this is the sine at frequency 1 over 2 pi. A little bit tricky. Put that in the homework just to be complicated. Okay, so that means that the Fourier transform of this thing, in terms of frequency, it has, well, of course, we can split that using Euler's. I won't do it, but I'll just write that here. We know a formula for sine, that it's 2 exponentials. So therefore, we have a frequency, there's 0. And here is 1 over 2 pi. We have some component there and some component here at negative 1 over 2 pi. That would be what would happen if it was continuous time. Okay, let me put the coefficients are not the same. This one is a 1 over 2i, and this one's a minus 1 over 2i. Okay, so they don't just have unit sizes. But actually, we just said that in discrete time, these each get periodically extended. So this one goes up here and down. So this frequency would be 1 plus 1 over 2 pi. Okay, and over here gets copied over here, which is going to be 1 minus 1 over 2 pi, and so forth. It keeps going. There's other copies out here. Right, and then let's do the other one. This guy gets copied up here sorry, this whole thing should be negative. Or what should it be? It should be 1 over 2 pi minus 1. I'll just write it that way. This should be 1 over 2 pi minus 1. So I just took this frequency and subtracted 1 to make that copy. Okay, I'm going to, this blue. And the green gets copied over here, and this becomes 1 minus 1 over 2 pi, and so forth. Minus 1 over 2 pi. Okay, and what we then said is, well, we can instead of, so 1 is, let me just first identify, 1 is somewhere, a half is somewhere here, right? Well, okay. So what I can do is I can say this is the same as just taking these two components here, pairing them up, and saying everything else is just copies of those. Okay. I started out with the sign of n, saying, well, here's the 2 original delta functions, and then I had to make these aliased copies. But now I can say, well, this is the same as identifying these 2 delta functions and saying everything else is aliased copies, and combining these back together and getting sine of 1 minus 1 over 2 pi n. Is there supposed to be a negative in there? Don't remember the problem. No, should be fine. Yeah. Okay. So, okay. So we see that one sinusoid can look like another sinusoid, although when we've moved away from complex exponentials, there it was aliasing was very easy to understand, and in sinusoids it gets a little bit more confusing. For example, if you increase the frequency of the sinusoid, that's going to decrease the frequency of this aliased one. Right? There's a little bit of slightly less intuitive things going on when you look at combinations of exponentials like sines and cosines. Okay. For fun, let's look at some other examples of aliasing. So here what we're going to look at is different, in videos you can get lots of fun examples of aliasing where you know the motion is doing one thing, but the video makes it look like it's doing something else because as a function of time, you're only capturing certain moments in time in the video. right? So you see what's happening here is this helicopter is flying without moving its propellers because it's defying physics. But in reality, it's just synchronized with the camera, right? So the camera is just getting a snapshot of it every time it hits a certain spot. Okay, and you see this is an example of aliasing where the motion is doing something repetitive, periodic, but it looks like it's not moving. So it's a specific case of aliasing where you've got the aliased sinusoid, it's being aliased to the zero frequency, the not moving. Here's another very similar sort of example. We've all seen these in movies and so forth. So you can get a lot of examples with things going in circles, right? So the wheel looks like it's going backwards. Are there any questions about what this has to do with aliasing? Because I know in the past, even after giving these examples, many people still wonder what exactly how does this relate to aliasing? What we're thinking about is this. It can be confusing when you look at images and video because there's a lot of ways to variables in a video. There's spatial variables for your signal, and there's time variables, right? And we're talking about aliasing along the time axis. In other words, things that happen with some periodicity in time when they get sampled in time. So the sampling here that's going on, turning into discrete time, has to do with the frame rate of the video, right? So there's a frame rate that's capturing samples of images discretely in time, and you're getting aliasing along that time direction, okay? I have some even better ones. I hope you'll like. Should I try to? What's fun is that in the video, it would look way different than it looks in real life, right? That's the whole key here. If you were watching this in continuous time, you wouldn't see this nice effect. Only on the video you see it because of the sampling rate. You would actually see these ripples falling, just like the water normally would. It's just some, if you splash a hose like that, you'll see kind of that shape falling down. But here, you're just getting a snapshot of it every time it hits the same spot on the way down. So what have they done here? So yes, they've gone to a. It's not slow motion. That's the cool thing. In the next video I have, you'll see that it's not slow motion. It looks like slow motion, but it's not. This is full speed, but it looks like slow motion. So yeah, you've changed the frequency of the sound. What they're doing to make the water move is they have a speaker there, and they have sound come out and make the water move. Okay, and they just changed the pitch coming out of the speaker slightly. Now they go to a lower frequency. You see that the lower frequency looks like a negative frequency. It looks like everything's going backwards. So this is not playing the video in reverse. This is playing the video forward. Okay. Here's another one. This will show you that what looks like slow motion is not actually slow motion. You'll see it very clearly here. Of course, in real life, he can't see this happening. You'd need like a strobe light or something to see this happening. You can do the same thing with strobe lights, and here's just a fun one. That this thing here, it's just stationary, but they're going to spin it and use strobe lights to get it to look cool. What's funny is someone's actually taking a video of this. So the strobe lights are making this, in real life, people watching it are going to see this effect. But because of the video, we actually see a second aliasing thing. We see these lines moving up that have to do with the synchronization between the camera recording and the strobe lights themselves in real life. Right? Now the regular lights come back on. Okay, so some examples of aliasing. All right. So we see that this can do cool effects, but it also could be something you don't want. And we're going to talk about when we don't want it and how to avoid it and so forth. Okay, talk about sampling a little bit more. Okay, first of all, we had examples of a self-similar Fourier transform pair. What we saw was that the sum over k of delta of t minus k, when you took the Fourier transform, you got sum over k of delta f minus k, the same exact thing back. Okay, that was fun. There are some other famous examples, and I mentioned one, like if you have something like e to the minus t squared here. Okay, so a plot of that is like this. This is the bell curve used in probability a lot, the Gaussian distribution. When you take the Fourier transform, there's some, I won't get the scaling right, but you get basically something, I'll say same here. Same up to a frequency scaling. I think you need a pi, either square root of pi or pi in both exponents to make it really the same. All right. So that's fun. And I have another one that I invented here. Say that tongue-in-cheek. Here's one. I will draw it for you. Oops. Well, let me draw it a little better. Okay, this thing, when you take the Fourier transform, put the F's there, you get back the same thing. All right. So this is the third very special function that does this. So can anyone figure out how I would express this with math equations? It's a sinc plus a rect. Okay, so this is sinc t plus rect t, and now you have a very general way of creating signals that have the same Fourier transform. All right, so there are many such things, but people usually remember these two, especially this one, because you need to know that for sampling. Okay, now, what I want to do here is derive this so we get some understanding of where this came from, because so far I've said we use delta functions in continuous time Fourier transforms. This allows us to kind of do everything in continuous time, understand how Fourier works. But you can't always plug in the formula. We can't plug this in to any Fourier transform integral and get this. Because I already said that you have, if the answer has delta functions in it, you have to do it in reverse. So if we want the Fourier transform, if we're anticipating that has delta functions, we should go this way to verify. But we can't plug this one in because that has delta functions as well. They both do. So none of the formulas are going to work. But we'll still get there. It won't be very hard to show that this is a Fourier transform pair. Okay. So what we'll do is just the following. We are just going to use what we already derived here. Up here, we said Fourier transform of this. Now, we're going to use discrete time to arrive at this continuous time process. So this discrete time signal, we know it's Fourier transform, right? What if I let f naught be 0? What is this signal? It's all ones. Ones everywhere. It's just discrete time signaled as 1. But what's its Fourier transform? So we'll use discrete time. So if x of n equals 1, then we already know that x of f equals, we should get the same thing that we just plotted here, except that that f naught should be 0. So this should be all the integers, right? Does that make sense? So I will write that now in formula rather than picture. That's delta f minus k. Okay, that's what we get. Now, we also know that, as we've talked about in previous lectures, that if we convert this discrete time process into a continuous time representation by simply replacing each of these numbers in the sequence by a delta function, right? Creating a continuous time signal out of delta functions, that preserves the Fourier transform. So we talked about that before. So in other words, we can do x of t equals the sum. So the general way of doing this is we say sum over k, x of k delta of t minus k. That's the general way of taking an x of n, converting it to a continuous time representation. But in this case, that's just this. So you can think of this train of delta functions as a discrete time constant function that's been converted to continuous time. Okay, and then voila, by what we know about this conversion process, the x of f does not change. And we have our answer there. Okay, there's another way to get at this. Well, notice what we did here. We had trouble with delta functions, so what we said was, let's go through discrete time. Everything works fine in discrete time, and then we can map it over to continuous time. There's another avenue to get at this exact same result. That is, let's start with a continuous time Fourier series. If you remember that we had this graph of all the different Fourier things, this table, and the kind of complementary opposite parts were the continuous time Fourier transform discrete time Fourier transform and the continuous time Fourier series. So we can use the Fourier series route to get at this, and all we would do is we'd say, remember, we're trying to prove that these are a pair in continuous time. We'd say, well, let's take x of t, which is periodic, and let's put it into the Fourier series. No problem with that. And there's, in fact, no problem evaluating the explicit integral to figure out what the Fourier series coefficients are. If I stick this into a Fourier series, can anyone tell me what the Fourier series coefficients are going to be? Yeah, they'll all be ones, because what I'm going to do is, remember, the Fourier series says integrate over one period. One period will contain just one delta function at t equals 0. Okay, so I just have a delta function at t equals 0, and I integrate that in the Fourier series integral. And integrating delta functions is easy. You'll get 1 for every coefficient. Okay. Then what I do is I convert the frequency domain from Fourier series coefficients to Fourier transform. And remember, we said you do that by taking the Fourier series coefficients and attaching them to delta functions. Okay, so two ways to get at this this formula. What we really are going to want is actually a more general formula for sampling at different rates. So this is like sampling at rate 1. And what I mean by that is the delta functions in time here occur at the integers. When in reality, we're going to be interested in getting delta functions that occur at any uniform intervals we want, because this is going to be our model of sampling, right? Sampling is you take a continuous time signal and you sample. So sampling, of course, is something like this. You have a continuous time signal, and you sample it at uniform intervals. And those don't have to be the integers in real life, right? They're just whatever frequency our hardware samples at. So to handle this mathematically, we're going to want to be able to talk about a train of delta functions at a different interval. All right, so that's pretty simple, but there's one catch to it. So how can we get that formula from this one? Okay, we can use the time scaling property of the Fourier transform. But don't forget, the delta functions, when they get squished, their magnitude changes. So we'll see that here. Okay, so the formula we want to derive is this, that the sum of deltas of t minus kts equals, so this is now a sampling period, sampling interval, right? That transforms under Fourier to sum over k delta, an fs, sum over k delta f minus kfs, where the sampling interval equals 1 over the sampling frequency. I'm just giving two different names to the same thing. We have a sampling frequency, we have a sampling period. All right. So this is what we want to show. This is important to remember, and it looks like we should just get this straight from the scaling property, but let's verify, because there's one catch in using the scaling property. So if we apply the time scaling to our starting point is this pair here. Okay, we're going to apply the scaling property, and that's going to say that let me give our pair, first of all, t minus k, f minus k. Okay, that means if we do time scaling here, let's do delta t over ts minus k. That's what it means to do, to scale these delta functions out so that they occur at every ts rather than every integer. Okay, and this should transform to, by our property, that should be ts times the sum, and then we scale the frequency. tsf minus k. Okay, this is what time scaling says will occur, right? So far, it does not look exactly like what we want. But then we have to say, well, I can rewrite that. That equals sum over k delta of 1 over ts times t minus kts. All right, which equals, by the property of these delta functions, that equals ts sum over k delta t minus k ts. Right. And the same thing over here, we would say that equals, keep our ts from before, sum over k f minus k over ts, and use the property of delta functions. Those cancel. The ts's cancel here. Whoops. Ts is gone. F minus k over ts. Okay, now we're almost done. Let's just, to get back in the form we had above, let's move this TS over to here, and let's rewrite 1 over TS as FS. Right, so now we get back at our final result. Okay, so we have a Fourier transform pair rule that we can just remember. You know, as you think about the Fourier transform more, or maybe already, you gain some intuition for what these, where these scaling constants come from and what they mean. For example, I think about it as I like to think about the DC component of a signal, and I say, well, if you spread your delta functions out in time, you sort of have a less DC component because the amplitude of your function is now occurring less frequently. Okay, spreading it out in time means low sample frequency. So in the frequency domain, the DC component is that delta function that's at 0. And so this Fs kind of represents that when Fs is low, the magnitude of that DC component went down. Okay, so there's various intuition you can gain for how to remember why there's an Fs there, for example. Conceptually, it doesn't become crucial to remember these constants. It's good to be able to do that, but for sampling, to understand sampling, those constants aren't going to matter, because what we actually want to know is if we can recover, and aliasing will be our problem there. So sampling is the process of creating a discrete time signal from a continuous time one in the following way. We are just going to let x of n be the continuous time x of n times ts for all n. Okay, so that's what sampling is intuitively. You're just keeping values of the continuous time function at discrete intervals. But as we said before, we have to understand this mathematically, it's easier to keep things in continuous time and say the following. You have your input, x of t, and it gets multiplied by a train of delta functions. In the last lecture, I just did t minus k. Here I'm going to do kts. Okay. So, and what comes out here now, as we discussed, is just the value of x at each of the delta functions multiplied by a delta function, right? So we end up with, so if this, so if x looked like this, then this is x. Let me do that in blue. Then the blue, what's going to happen is you're going to get delta functions. Let's say times 0, times ts, times 2ts, and so forth. So after doing this multiplication, you're going to get these delta functions, right? That's your output of this sampler. And you see why this is a, now in reality, of course, and we'll come back to this in a bit, we actually, when you finish sampling, you actually just end up with a sequence of numbers. You don't end up with these delta functions, but you see there's a simple mathematical conversion between these. This sequence is just the magnitude of these delta functions listed out, right? But from a Fourier point of view, it's going to be very helpful to think of this continuous time process, okay? Because the question then is whether we can recover and interpolate. And we already saw that we could, but let's go through it again. We can in certain cases. So let's assume x of t is band limited. And I'll tell you what that means. That means that in the frequency domain, you have some section of the spectrum, some section of frequencies, where the magnitude may be non-zero. Okay? But then outside of that range, you have zero magnitude in the Fourier transform. Okay? Well, let's say that the maximum frequency you have here is B. So you've got from B to negative B, the spectrum lives in that range. We call this band limited. In fact, people would often refer to this as having a bandwidth of B. Now, there's a more general way to think about bandwidth. I'm here just saying that the spectrum has an upper bound on its frequency. Okay, you could say, well, actually, let's say more generally, upper bound FU and lower bound FL, and then you have that there's the whole spectrum lives in this range. Okay, and then they would say the bandwidth is this difference. Bandwidth equals FL minus, oops, oh, I wrote that wrong. Obviously. FL here, FU here. So you'd call that the bandwidth. Okay, but let me point out these pictures may seem kind of different because here we're saying, well, this width is actually twice B. Okay. It would often be helpful to call this whole thing 2B the bandwidth. All right, but typically B is called the bandwidth, and here the upper frequency minus the lower would be called the bandwidth. But notice that even in this case, if your signal is real, then that means it's symmetric in frequency. So even in this case, you should, let's say here's 0. Somewhere over here, you'd have a copy of that. So here, you have the same issue, that that even though you're calling the bandwidth this width, the space in the spectrum that's actually taken up is double that when you count the plus and minus frequencies. Okay. In fact, that doubling is exactly the 2 in the Nyquist theorem. All right. So if we instead were to call the bandwidth the whole space, positive and negative frequencies, then the Nyquist sampling rate theorem would be even simpler to state. What would it be? If anyone knows Nyquist. We haven't talked about it yet, but I know some of you know Nyquist sampling theorem. Well, maybe not. Okay. So, what was that? Here we're talking about real x of t. It doesn't have to be, but yeah. But for this example, it is. Oh, I didn't draw that mirror very well. This should be a mirror here. There we go. Okay. So, okay, let's go back to our simple definition of band limited. We don't have a lower bound. We just have an upper bound on the frequency. Okay, so and that's B. So this was a little aside here. Okay, so assuming it's band limited, then let's say we sample. Okay, so take x of t times this thing here. Okay, delta. And this product here, the Fourier transform of this, will be easier to think about. And that's going to be x of f convolved with the Fourier transform, which has an fs. Right? I'll bring the fs out front by linearity. F minus k fs. Okay? So it's this convolution, which is very simple to think about because what we have is we have something like the following. Some spectrum like this, and it goes up to B. not higher than B. And when we do this convolution, let's say this I'll call green. That looks like this. And these now are occurring at Fs and 2Fs and so forth. So when we do the convolution, we're going to get repeats of the spectrum. Okay. And even though this is different now, okay, so obviously once you've done this multiplication, you're not going to get back the x. I mean, this will not be x of t. But what we see is it's not much different than x of t in the spectrum. In fact, you can pick out the spectrum of x of t very easily. So in some sense, we haven't lost any information. All right, if you sampled high enough for band-limited signal, you haven't lost any information. How high did we have to sample, though? Because there's another case that could happen. We could have the following case where it was like this, and the sampling frequency was lower. And when you do the convolution, you get a sum of these types of terms, right? And what's happened now is this whole range of spectrum has been corrupted, meaning that you can no longer separate which part of that signal came from, for example, when you're looking at this particular point right here, B plus a little bit. Sorry, this is B. This is Fs. So take this spot right here. What is this? This is the first frequency that starts to get corrupted, all right, due to the sampling process, due to the aliasing. What frequency is that? I'll give you a hint. Yes. Thank you. So this is Fs minus B. Okay. So if Fs minus B is smaller than B, then you get some corrupted part of the signal. There's no way to go separate that back out. Okay. Well, of course, so no aliasing. We call this aliasing. I'll write that here. This aliasing. Okay, we get no aliasing if Fs minus B is greater than B. That means if Fs is greater than 2 times B. All right. So this is called the Nyquist sampling rate. Twice the highest frequency of your signal. Okay, and we see that if we have that, we do not get overlap in these copies of the spectrum. Okay, so how then, suppose we sample at a high enough frequency. We're saying that we didn't lose any information. How can we recover the signal? We did talk about this last time, but go ahead and explain it. Now tailored to the sampling frequency. What should we do here to recover? Let's say we're in case 1, where we do not have aliasing. That's the good case. It means we've sampled in a way that we should be able to recover. How do we recover now? What we're talking about now is we have this picture of sampling. We've done this multiplication. The question is, can we put something here to reconstruct so that out comes x of t again? In other words, is this sampling a reversible process? Yes? Absolutely. So we just want to keep 1. In fact, if we want it to be exactly like x of t, we better keep the 1 right in the middle. Of course, if we kept another one, we'd still have all the information, but we would need to process it to get it back to being x. But if we keep the one in the middle, it's already exactly x, right? So we should put a, and we keep saying this word filter. We want to put a filter here. But yet we haven't really talked about filtering. So let me just mention now, what we mean by filtering is designing a convolution, designing a linear time invariant system that will perform some operation. Okay, so what we want is in comes this x, the sampled version of x, and we want an LTI system. And we can design LTI systems to do all sorts of things, although we know that all LTI systems can be understood as doing one thing in the frequency domain. What does an LTI system do in the frequency domain? Attenuation, amplification. In other words, it just multiplies in the frequency domain. Why is that? Because LTI means we're doing a convolution with some impulse response that we can maybe design, right? Okay, but convolution in time is multiplication in frequency. So it means that we might as well design a capital H of f, okay, the Fourier transform of the impulse response. If we design H of f, then whatever comes in frequency domain will be multiplied by H of f. And notice that this band, what we've been calling a low-pass filter here, low-pass just means that this is actually an ideal low-pass filter. There are many low-pass filters. Since it's ideal, I better drop it nice and straight. Okay, this would be the rect function in frequency. That's an ideal filter, an ideal band-pass filter. And if it's passing low frequencies and getting rid of high frequencies, it's a low-pass filter. The ideal low-pass filter, okay, is simply H of f equals something to do with rect. Now let's be a little more specific in this particular case. What cutoff should we have in frequency to recover x after we've sampled at fs? Okay, you can see that we can do all sorts of things. We could use b if we wanted. Okay, but it's actually, I mean, it's simple enough just to say let's have the cutoff be half of the sampling frequency. As long as we sampled above Nyquist, there should be a gap here. And half the sampling frequency should separate out these two signals. Okay, so let's choose that. This is fs over 2 and minus fs over 2. And if we want to be a little bit technical here, let's look at there was one thing that actually happened to the height of the signal. Now, remember when we sampled, we not only did this convolution, but we have an fs here. Okay, so in other words, we actually, this first part here was actually not just x of f, it was times fs, right? That's what that inner block became. Okay. So if we want to undo that, of course, undoing a scalar multiplication is trivial. That's just amplifying the whole signal or attenuating it. It's not really qualitatively going to change what we're doing, but let's go ahead and include it. So what we would like is that this filter have magnitude 1 over fs. Okay. Okay, so let's go back here and finish it off and say what we actually want is we want a low pass filter. Okay. And what did we say? Well, let's write this as a formula here. What exactly is it? Rect of something. So we want to get rid of, we want 1 over fs, okay, so to get the height. Rect what? Close. There's no 2 because rect already only goes up to a half. So rect goes negative half to half. So if we wanted to go negative fs over 2 to fs over 2, we do over fs there. Okay. So what does that mean h of t is? It's the inverse Fourier transform of this. Think of fs t or we can write sinc of t over the sampling period. Okay, so it's actually a very nice, just like we saw in last lecture, it's a very nice process to reconstruct x. We convolve with sinc of height 1, but now because we changed the sample rate, the sinc gets spread out to be the width of the samples. Okay, right, just like we would expect. So remember, convolving with sinc is the sinc interpolation that we drew in a picture before. So we're doing a sinc interpolation. So everything's the same. We just included the sampling frequency this time through to repeat this derivation. Okay, now what we really want to... So that's what's the good news. If you sample above the Nyquist rate, then you can fully reconstruct, right? What if we don't sample above the Nyquist rate? Then what are we left with? Well, we're left with a signal that's now corrupted, right? You actually, I think in lab 1, this was one of the things you did. You made a sinusoid, and then you took a subsample of it. Okay, think of this as sampling in continuous time. And you went to the lowest possible sample frequency before the sound started being really bad. Do you remember doing this? And if you did it the way I did it, you hit a point where it starts sounding way different. Okay, you can keep reducing the sample rate to a point, but once you get past that point, the pitch actually changed. Did anyone do that? Reduce the sample rate enough where the pitch started to change? Okay, that was this aliasing. What happened was, you reduced the sample rate. So the pitch was like a delta function somewhere here. You reduced the sample rate so much that the other copy of that delta function, the negative copy of it, came over and started and became lower in frequency. It switched places as you reduce this sampling frequency because the two copies come together, right? And so it switched places and became an artifact. What was a higher pitch all of a sudden was interpreted as a lower pitch by the speakers. They couldn't tell the difference, right? Okay, so there's something you can do to get rid of this aliasing artifact even afterwards. Like you've already sampled, there's no going back. You have a sampled signal and you say, uh-oh, I sampled too low of a rate, but I can't do anything about it. Well, if you know something about what the original bandwidth is, then we at least can calculate where the aliasing will occur. It'll occur in this range, fs minus b to b, right? So why not go and cut this out with a filter? You can cut that part out. All right. This is sort of a post-processing way of fixing the aliasing. All right. What's the difference then between that? Actually, I'll give you two alternatives, and we can think about the difference here. So the real approach, in what you actually would like to do about aliasing, let's say your sample rate is constrained. And let's say your signal has a bandwidth. Oops. B. And let's say that 2B is greater than Fs. So you're not going to be able to just sample this thing and not worry about it. Okay. And you don't want aliasing artifacts. Okay, they're no good. So one approach that's actually done so the way you actually sample is you do this. The signal comes in, here, x of t. You first, before you sample in continuous time, you do a low-pass filter. Get rid of the parts that are going to cause you aliasing. You say, yes, I had a signal that had high-frequency components. I would like to keep it all, but I can't. So I'm going to cut it off at the Nyquist, at half the sampling rate, right? Fs over 2 minus Fs over 2. So you do a low-pass filter before you sample, right? And then it goes in here, and then you get sampled. At the rate Fs, no aliasing. but you did lose part of your signal by doing this. Okay, but we can compare whether that was really worth it or was it any different than if I just took the samples. Okay, so let's do the comparison. So what happens in this case is your signal was like this, went up to B, but what you actually did was you cut it off. You cut it off like this at Fs over 2. Okay, and then then you have this new thing that looks like this. Missing parts of the signal, just the price you pay for this sample rate. But then when you actually sample and you copy this over, you don't get overlap, right? So you can still recover. There's no aliasing, no corruption going on in your signal. Okay. Now, what if I just said, well, forget it. I'm just going to sample, not worry about it, and then maybe afterwards try to remove the bad part. And let's see the difference here. So you could take x of t, sample. Let's look at what you would have to remove. So, and then we'll filter in discrete time. We'll just do some sort of removing of things in the spectrum that we don't like. Okay. So here what you have is you have your original thing that went up to B. You sampled at Fs. So what that did was did this type of thing. Okay. You corrupted this whole part of the spectrum from there to there, from there to there. And now we're saying, well, let's try to remove it. We don't like these weird sounding artifacts if it was sound or whatever. So I'm going to cut it out with a filter that looks like this. Of course, now I'm in discrete time. If I'm doing a convolution with the signal in discrete time, the impulse response of that signal, any Fourier transform is going to always be periodic. So any filtering in discrete time will be some periodic thing. So here's the discrete time low-pass filter would actually look like this. That's fine. Okay. And what I'm going to do now is let's look at what I end up with after filtering. I end up with something with much less of the spectrum left. Okay, so here were the two ways to do it. One way was I filtered out the offending part in continuous time before sampling. And that gave me a result in discrete time that looked like this. If I want to then reconstitute my signal, I would filter out these parts, and I would just have this. And although it's not exactly what I started with, it contains most of the spectrum, right? And so this contains spectrum up to Fs over 2. But if I just sampled and got aliasing, and then went afterwards and tried to remove the aliasing, then how high does this go? It goes to Fs minus B, which by assumption was less than Fs over 2. So I end up with less. So you want to remove the aliasing before you sample. You always put an anti-aliasing filter before you take samples. That shows us that here's the actual way, like an audio system or some digital signal processor would go from continuous time to discrete time. They would actually take your signal, x of t, they would do a low-pass filter in continuous time. This is continuous time. They would sample. Okay, this is a low-pass filter. It looks like this. And out would come some, on our model, it's some delta functions, but in reality, you just make that a list of numbers, right? And to redo it, what do? You take this, let's say x sampled of t. You take the sampled version. You first, actually, let me say it this way. You take your discrete time signal. You first make it a continuous time representation. So meaning that you take your sequence of numbers and you actually make a, you put it back into actual delta functions. Okay, it's a train of delta functions. And then all you do is you low-pass filter. Continuous time, low-pass filter. It's the same one, except maybe there's an amplitude gain. So in other words, going back from discrete time to continuous time is basically the mirror image here, assuming we sampled above Nyquist, right? So you always put this thing here. This is your anti-aliasing filter. So in audio, for example, CD audio samples at 44.1 kilohertz. So if you have everything ideal, low-pass filters are ideal, you should be able to record sound up to half that frequency, right? 22 kilohertz. The human ear does not generally hear above 20 kilohertz. That's why CD audio was designed this way. Even if there was signal up there, you wouldn't hear it anyway. But you still need the anti-aliasing filter, because if there is signal up there that you can't hear, and you sample without this filter, then the aliasing is going to bring that stuff down to the part of the range you actually can hear. And it's going to be garbage. Okay? So you still want to filter it out, even though you wouldn't be able to hear it in continuous time. You filter it out so it doesn't cause aliasing. And then you sample. Right? Okay. Any questions about this? Yes? Yes? That's a good question. See that in this, and you do have a problem set related to this. So let's talk about it for a second. You could get away potentially with a smaller sample frequency than double the highest frequency. So typically we say double the highest frequency is Nyquist, right? So that would be 2 times this FU. But clearly there's something more fundamental about the gap here than just talking about the upper bound. Okay. There's another rate that's called the Landau rate. Let's write it here. Landau rate. Let's say U. Which is just the sum of all the interval widths that the spectrum is contained in. Okay, so in other words, here the Landau rate would be 2 times FU minus FL in this case. Okay. Now that is a lower bound on how many samples you need. It's not always possible to sample this at as low as that rate and still recover. But that's a lower bound, and if you do something called non-uniform sampling, then this would be the achievable. You could get down to this rate. Okay, so in some sense, this is more fundamental, but we still call the Nyquist rate 2 times FU, because just to be simple, we say it's twice the highest frequency. We don't assume we know anything about the spectral content below that highest frequency. Okay, to check what other frequencies would work here, let me give an example of a frequency of a sampling that would work. Suppose that FU is greater than half of FL is greater than half of FU. Okay, so what I mean is just kind of like the picture indicates. FL is closer to FU than to 0. Okay. In this case, I can at least show you that I do not need a sample rate of 2 FU. I can get away with just FU as the sample rate. Okay, let me show how. Let's just check what happens if I sample. Remember, I'm convolving with delta functions in the frequency domain. So let's sample at, let Fs equal Fu. So that's not the Nyquist rate, right? The Nyquist rate would be 2 times Fu. So we're going below the Nyquist rate. So our sample rate is here. But watch what happens when we copy this spectrum. I'm going to use green for the copies. I take that whole spectrum, which is not drawn very symmetrically, but anyway, take the whole spectrum and center it now over here at FU. And you get the other copy of it goes right here. And the upper end of it is like here. Okay, so there's my next copy of it. Right? Let me draw one more copy. I'm going to go now to the left. And I'm going to draw the copy that has to do with from the left here. And that's going to look like this. And it's going to have something way off to the left that's on my words, so I won't draw it. Okay? And then it'll just be repeating. So you can check what happened when I did the sampling. I got this. Okay? Can I recover my original signal from this? Yes, I can. Okay, I can. Again, I'm going to take into account, in order to recover, I had to know that the spectrum was contained in this range. I don't need to know what the signal is. I just need to know the spectrum was contained in this range. So I know there was no aliasing, which means if I make a filter that comes and just cuts out all of the extra parts, so my filter now should look like this. Should be like, yeah. So if I make a filter like this, right, where those are the pass bands of the filter, it's 1 in the spots I've drawn and 0 everywhere else, then I get right back to my original signal. Okay, so I was able to recover. So your problem set is like this. You should try different sample rates, draw pictures, and see where you get aliasing, where you don't. All right, so it's a special case where you don't just know that the signal is in the lower frequencies. All right. This would be like, of course, you have to build the sampler and the reconstruction hardware with this in mind. You have to say, oh, I want to be able to recover signals in some range, so therefore I'm going to build it in a different way. The typical way, like if you take any sound card, for example, they're always doing this low-pass filtering and just assuming that you care about the low-frequency stuff. Okay. Another example of aliasing, and let me go here, is images. So you hear about anti-aliasing filters in images. Let me just explain partly what that means. Now we're not talking, before we had some video examples where we saw aliasing in time. Well, now let's talk about images, so no time. But we're going to look at aliasing in space now. So think about like when you took Fourier transforms of images in the labs, you were dealing with space was your, the x and the y were your independent variables, right? So what can happen if you sample an image, you downsample, so one way to compress would be throw away a bunch of pixels, just take a few pixels, right? You can get funny things like this one down here. You see this? Can you guys see that artifact? It looks like it's wavy. This is just a brick wall. There's no waviness to it, but the samples that you keep in the picture just line up with the pattern of the brick just right, that you get this artifact. This is, in fact, aliasing, because there was some high-frequency content in the original bricks that you cannot capture with the lower pixel rate. Think about taking fewer pixels is like sampling, right, in a two-dimensional signal. So now that you have fewer pixels, you can't represent as high of frequencies anymore. But even worse than losing the high frequencies, you've actually corrupted the lower frequencies that you can represent, because some of the high-frequency stuff aliased down. Okay, that's what's happening here. So you can avoid this. How would we avoid it? Low-pass filter. When? After we have this image? Yeah, well, you'd have to go pretty low, because that's a very low frequency. You lose almost everything here. But if you did it before, then you avoid it, and you don't lose the stuff that you can keep. So you want to put the low-pass filter before you do the downsampling. Okay, before you do the sampling, your low-pass filter. And that's why you have these things called anti-aliasing filters and stuff. You mean like, okay, you're saying do a high-pass filter, maybe some bandpass type of thing? Or yeah. The low frequency noise, though. Well, first of all, in an image, if you cut out the low frequencies, you wouldn't like it. You actually generally care more about the lower frequencies than the high frequencies. But the reason that this artifact looks like a low frequency, it started out as a very high frequency, but only after aliasing it became low. Now, you could build something either for signals in time or for images that just preserve high frequencies and don't care about low frequencies. You'd have to build it differently because first of all, before sampling, again, you would pass only the band you're interested in. And then you would sample at a rate high enough to preserve that information. But then when you represent, let's say it was an image, you want to go display it now. You have some numbers, now go and display it. You need a way of displaying it that recovers the high frequencies. In sound, what you do in sound, to get back to the original continuous time signal that you want, the recovery is like this. You just low-pass filter. Now in this new system, you would replace that with a high-pass filter. For images, that's a little bit weird to think about, because for an image, the way that you actually convert these numbers back to an image is you just use little square pixels, right, and you color them, which is very much like the zero-order hold that we talked about last time, of trying to reconstruct a signal with just rects. Okay, and that's closer to a low-pass filter than a high-pass filter. So you would not want to, your protocol for displaying images wouldn't be anything like this if you wanted to preserve high frequencies. Okay. Let's see. Okay. Let me give you a couple of something related to the problem set before I forget. And then maybe we'll talk about downsampling for a second. Okay. So we're not going to really talk about filtering until a few weeks from now. I changed the order of things. We'll come back. We're actually going to take a break from Fourier transform for a couple of weeks. And then we'll come back to it. All right. And so we'll do filtering after we come back to it. But I want to mention one thing that's a nice little observation. That is, if you have, suppose you have an x of t that's even. What do we know? And it's real, right? Even and real. What do we know? Can you recall? What do we know about its Fourier transform? Some properties it might have. Does anyone remember? It's also even and real. Awesome. So if it's even and real, what is the phase? We often like to separate a Fourier transform into magnitude and phase. So what's the phase of an even and real number or function? Right. So this is so we have some h of, so we want to know the magnitude of this the phase of x of f. Well, if it's real, then the phase is 0. Okay, technically, the phase could be pi as well. It could also be 2 pi, but we consider 2 pi the same as 0. Why could it be pi? Because x of f could be negative, all right? But I'm going to say this is 0 phase, even with that little caveat that it could be pi phase as well if x went negative. But this is generally called 0 phase. And the reason this is important is because as when we get to talking about filters, we'll want to design things in the time domain and understand their properties in the frequency domain. And one of the techniques is to always design even, meaning symmetric impulse responses. That way we know the phase is 0. We can say certain things about it. Suppose that we then have an x of t. Suppose that we look at x of t minus that. Okay? So if x of t started out even and real, then x of t minus any number is going to still have a symmetry, but that symmetry will be shifted. Okay? But what happens there is when we take the Fourier transform of this, well, we have a property for time shifts, right? When you do a time shift, you get e to the minus I 2 pi f capital T times x of f, right? And notice what happens to this. This only contributes phase, not magnitude. So this time shift only changed the phase. But we just said the phase of x was 0. So what's the phase now here? Phase equals, When we've taken something that's symmetric, but it's no longer symmetric at time t equals 0, it's symmetric at some other point in time, real valued and symmetric about some cap t, then what do we know about its phase? What? It's just exactly minus 2 pi. I'll change that order so it looks like a linear function. It's a linear function of f. Okay, this is referred to as linear phase. So this will be interesting in filter design. We'll just barely talk about it a little bit in a few weeks, but also it's interesting on your problem set because there's a problem where you have to say certain things about the Fourier transform of a signal, and you're given a hint that you don't need to do any integrals. Okay, and so for every step you should be looking for some simple trick to figure out the answer. And one of them is going to require that you notice a symmetry. Okay, and you use something like this. All right. Okay, let me make a last comment about sampling here. Discrete time downsampling. Okay, downsampling means you have some signal and you want to just take, let's say, every other sample from it or every fifth one or something to have a shorter signal now. You don't keep all the samples. We want to say, well, what can you, for example, can you recover, fill it back in by interpolating? Just like the continuous time version of sampling. And here's what we mean by that. If you have some x of n, and you end up and you end up only storing x of kn, where k is some positive integer. So you only end up storing every kth value. Well, we can represent that in a very real way as a product with a train of delta functions, just like sampling was. So here we say this is delta n. Whoops, it's a discrete time delta. Much easier to understand. N minus. Let's not use k. Let's say kappa n. Okay. So we're going to sample. So what is this going to return? This is our downsampled version of n. This means that if you have some sequence of numbers like this, okay, this is our x of n. And if we have now our sampler, we can think of, if we're just going to keep some of those samples, we can think of that as multiplication with delta functions that are now spread out. So 0, n, 2n, so forth. Okay. If we multiply these, what we end up with is we lose everything in between the samples. We only keep these, and the rest becomes 0. Right? So this is a good mathematical way of understanding what downsampling does. And downsampling says we just keep these ones I circled in green. And what I've done is I've drawn a mathematical operation that would at least be almost the same thing. It would be making everything else 0. Okay. The only last step to actually downsample would be to just throw out the zeros, shrink it all together. Okay. But this again, because of the convolution property, this says that x of f this time it had, because it's discrete time, had to be repeating. Okay, so it had some spectrum. And we need to know then what is the Fourier transform of this delta function. You have this thing here, sum over n, sum over k, delta n minus k n. Okay, and this ends up just being delta functions spread out by 1 over n. Okay, And with the height, that's actually 1 over n. So what we get then is we use the same kind of analysis that we did with continuous time sampling to say, do I get aliasing? In other words, once I copy this over, once I do the convolution in frequency and I add it all up, do I get aliasing? And in my picture here, yes, this all aliases. Everything aliases. This would, at that sample rate, that downsample rate, I've corrupted all of my frequency content. However, if this downsample rate was high enough, these would be spread out enough that they don't overlap. And if they don't overlap, we can do the same thing to recover. To go back to the upsample, we can then do a low-pass filter, okay, a discrete time low-pass filter to get back to the high frequency stuff. So this is the difference between doing the naive thing, say in MATLAB, to downsample. Let's say you have a CD sound, and you downsample by just taking every third sample, right? That's going to cause aliasing because your sound probably fills up the whole spectrum, okay? But if you say resample, which we've used in the labs, right? When you did Shazam, you said resample to 8 kilohertz from 44 kilohertz. And you resampled everything. That command, resample, the difference between that and just writing code that says take every however many samples you'd have to do that conversion. The difference is that resample does a low-pass filter first. That's the only difference. Resample does a low-pass filter and then a sampling, which is called decimation in discrete time. Just does those two things rather than the one to avoid aliasing.